seminar series. Today we are very excited to have Appoorv Vikram Singh as our guest speaker. Appoorv is a third-year PhD student at NYU, where he is advised by Christopher Musco. His research interests lie at the intersection of theoretical computer science and statistical machine learning. Currently, he is working on problems in the area of spectral estimation of matrices in sublinear time. He has very kindly agreed to give a talk titled Moment, Random Walks and Limits for Spectral Approximation. So let's welcome Appoorv and all yours.
Thank you. So, yeah, happy to be here. And I don't know how many of you know, but I think only Anand and Ramesh know, but I was in IISc from 2017 to 19, so it's great to be back here. Okay, so yeah, the title of the talk is Moment, Random Walks and Limits for Spectrum Approximation, and this is a joint work with Jin, Christopher Musco and Aaron Seckford. So we'll set up the problem first. So you are given a weighted graph G with the normalized adjacency matrix A. And the eigenvalues of A is what I'm going to call the spectrum of G. And the goal is to estimate the spectrum of G. So first of all, you can notice that you can exactly compute all of the eigenvalues in approximately n to the 2.35 time using the full eigen decomposition, but it is very expensive for large values of n. We are ideally interested in sublinear time algorithm, and here sublinear means small o of n square, because just to read off all the entries of the matrix you need order n square space and time. Okay. So when
you what is the normalized? What's the normalized?
So like if you think it's the d minus half a d minus half like that. So basically, if you think of adjacency matrix G, then G divided by the degree D is the normalized adjacency. So in a D regular graph, so G divided by D.
And like you mentioned, just reading the matrix would take n square time, right? So little o of n square is after reading the matrix.
No, so yeah, we'll see how we get to that here. Yeah.
How do you know the eigen decomposition?
It's a symmetric matrix. Adjacency matrix, yeah.
But the regularization is by D, which is where D is the max degree.
So D is basically a diagonal matrix with the degrees on the diagonal. So degree of each. Okay. So G is basically adjacency matrix. So the normalized adjacency, which I'm going to call A in this talk, is basically D minus half A D D minus half, and so D is a diagonal matrix. So DII is equal to degree of the vertex. Okay. Should I push it back? Okay, so yeah. So first of all, some motivation for why we are even interested in this problem. So generally, like people have studied these extreme eigenvalues of graphs like lambda2, which tells you how good of an expander a graph is. But like here, we are interested in the whole spectrum, and the spectrum also contains some important information about the graph. For instance, it contains insights into the community structure of graphs. So think if you have a very big network graph, then if you find a lot of repeated eigenvalue, those typically correspond to some repeated structure in the graph. It's called motifs. Like a lot of triangles in a graph would lead to many eigenvalues being repeated. So that, and yeah, like some people use it for to like parallelize GPU-based methods for eigen decomposition, and also you can verify the general generative model assumption. So suppose you have a Twitter graph and you say it follows some power law, so you can, if you just compute this approximation to the eigenvalues, you can just see if it verifies those assumptions. Yes.
Why does a partition equal?
It just tells you that there's a way to relate it. Lambda 2 to lambda k will tell you the quality of the partition.
There always be partition.
I mean, you can always partition, right? Like, if your size of the graph is more than k, I guess. Yeah.
So time was not a concern, then you can compute all of these.
Yeah.
What's the time we need?
This
Exactly,
much.
you have to compute all of them.
Approximately this much. Yeah.
Okay. Lambda 1 to lambda k is the top k of lambda 1.
Yeah. Lambda 1 to lambda.
You're interested in only one of these quantities. Can it be the faster or still?
Yeah, like I think I don't know if you're interested in the middle quantities like lambda I somewhere in between. I don't know about that, but the corner ones you can, like lambda 2, for instance, you can do possibly using power iterations.
Yes, where
But yeah, I mean, I haven't told what little O of n square is, but yeah. Okay. So yeah, I mean, so since we are asking for little O of n square, so there's a trade-off between accuracy and time here. Like I want to get an approximation to the eigenvalues, but for a faster running time. So we'll see what do I mean by estimating the spectrum. So for that, there's this notion called spectral density of a graph. So you are given a graph G. What you can do is just make a histogram of its eigenvalues, right? Like on x-axis you have the eigenvalues, on y-axis you have the frequency, and you can normalize the frequency to make it look like a probability distribution. So basically, each of the eigenvalues gets like weight of 1 over n, and formally you will just write the spectral density is 1 over n summation delta of x minus lambda. Here, delta is the direct delta. Yeah.
This is a discrete.
Yeah. So
the connection with the previous original problem?
So I just want to define this notion of what do I mean by estimating the spectrum. So I told in the first slide that I'm interested in estimating the spectrum in sublinear time. So I want to tell what do I mean by estimating it. Okay.
And so just to understand, there's an actual frequency. It need not follow normal axis.
Yeah. This is of a hypercube graph. But
and then like you output some vector lambda 1 to lambda n, and you just measure the Wasserstein distance between your output.
Yeah. So your goal is to output a distribution Q such that the Wasserstein distance between P and Q is less than epsilon. And so I'll just quickly tell what Wasserstein mean. So basically it means it's also called the Earth's mover distance, right? It's an Earth. So it's the minimum over all schemes of moving. So you have this distribution Q, how much mass you have to move from on the x-axis to get to distribution P. And in our case, it turns out to be something very nice. Basically, output the eigenvalues lambda n dash to lambda 1 dash. So that Q of x, you can write its spectral density, but this formula is what I'm interested in. It's like the Wasserstein distance between P and Q is basically the difference, L1 norm of the difference of the two eigenvalues divided by n. So, for instance, if you see in this figure, like the blue are your actual eigenvalues, and the dotted ones are your approximations. The red ones are your approximation, and what it means is how much mass you have to move these red distribution to get to the blue distribution, and we have written there nail the peaks. So what it means is basically wherever the eigenvalues are peaked, I want to get very good approximation to that, because that's a lot of mass there which you have to move to get to this one. But for instance, I can make a lot of error here because there's only very little mass there. So I don't like, I'm fine with making some errors there, but I think of Wasserstein distance in this case as like just nailing the peaks of the distribution.
There could have been different measures. Why is this interesting?
Yeah, people have looked at this, and also like I saw it in appearing in some chemistry work as well. Yeah. Yeah. What? So it's basically like it's a way to formally write this probability distribution. Think of this as those red dashes there. Yeah.
Somehow all the complications going away. The final formula is very clear.
Yeah.
What is happening is not.
Yeah, I mean.
So the definition of this Dirac delta, right? It's at x equal when the argument of the delta is 0. That's when the value is 1. Rest of the time is 0. So only then, like in Q of S, if you are able to get lambda I prime exactly, then you are having some non-zero boundaries.
So Q of X is basically uniform across lambda 1 to lambda n. What that is?
So P of X was lambda into lambda 1 to lambda n. Q of X is lambda 1 dash to lambda n dash.
But all uniform.
Yeah, uniform mass over. But like these can be repeated, that's why it looks, lambda i's can be repeated, that's why it looks peaked here. But yeah, I mean, it needs a proof that why the optimal way to transport this P of X to Q of X is this. But I'm not showing that here.
So why could it not be that lambda I plus 1 is transported to lambda I?
Yeah, I mean, it could be, but like this is the optimal. Like, yeah, there is a proof. Like, I'm not planning to show that here.
It's a simple proof. You can have it for like 0-1 kind of function.
Yeah.
So also just to clarify, when you said nail the pixels, you're saying the essentially the eigenvalues with a higher frequency are more important in our estimation as an estimation target.
I mean, it's sort of what it implies. Like, I just wanted to give like what it would intuitively mean to approximate in Wasserstein distance. Yeah, I mean, there's nothing technical. Like,
Yeah.
One of the eigenvalues is less than epsilon value. Kind of ignore it.
No, there can be many of them less than epsilon.
Total additive value is epsilon n. So one is really less than epsilon, you can ignore it.
I mean, that ignore it in the sense approximated with 0. Yeah. So 0 is also an eigenvalue.
Eigenvalue can be negative.
Yeah. It's from -1 to 1.
Is that an idea you should use? Like, because I think there are efficient methods to compute the top and the bottom.
Yeah, but like a lot of stuff happens in middle also, right? Like, for example, this is of a hypercube.
Right.
Okay. So this is what I mean by estimating it. So there's some existing results on this, and now it's coming back to this question of what I mean by small O of n square. So you're given this graph G with spectral density P, and what you're given is the random walk access to G. So what you assume is that you can start at a random node and transition to a random neighbor with probability proportional to the edge weight in order 1 time. Okay, so you can do random walks on the graph, so you don't have to look at the whole matrix. And for that, of course, the goal is to output Q such that Wasserstein 1 between P and Q is less than or equal to epsilon. And there are basically 2 sublinear works on this. One is by Cohen-Steiner et al., which outputs a distribution Q in time 2 to the power order 1 over epsilon. And Braverman et al., which outputs a distribution Q in time n over epsilon to the 7. And yeah, like a surprising thing in the first result is it is independent of the size of the graph. But it has this undesirable exponent of 1 over epsilon. What?
Is this AC solar?
Yeah, so CS is Cohen-Steiner, K is Wei Kong, S is solar, and V is Valiant. Yeah.
In the first case, we looked at nominal factorization using degree. In the weighted case, they do something.
Yeah, so degree would be the sum of weights on the vertex. Okay. So so the focus of this talk is basically understanding this Cohen-Steiner et al. Result. So basically, their algorithm takes 2 to the power order 1 over epsilon steps of random walks on the graph, and they output, and therefore the running time is 2 to the power order 1 over epsilon. Basically, that's the bottleneck, and our result shows that this algorithm cannot fundamentally be improved. So I'll make it clear what it means, but this you're bound to have this 2 to the power order 1 over epsilon is the result. So first I'll explain how they're
Random walk is it you're doing a matrix vector product to include that?
Yeah, but matrix vector product, yeah. But so you do a matrix vector product, and then whatever vector you get, just sample one entry from that according to the weights.
But in the matrix vector product, we take some
Yeah,
dependence on it.
yeah. So yeah, that's why I said like yeah, you need the. I just assume that this can be done in order one time. Yeah. Arbitrary.
So if you do a random momentum, it's a very local information, right? And you only see. If you do a matrix vector, what kind of thing?
I mean,
your lower bound also holds for matrix vector queries?
No, so I think what I understood from her question was that a random walk can be seen as a matrix vector product.
Yeah, but like in terms of like intuitive information sense, like this single, so normally you can do this random walk, single random walk by this matrix vector query like EI kind of, right?
Yeah.
But if you choose this vector that you're multiplying like very carefully, it can give you potentially lots of extra information, right? And
yeah.
it can give you more structure in a small amount. But as your lower bound also hold there?
Yeah, I mean, if you generate the entries of vector like using these random walks, then it will hold.
No. So like, suppose I can choose that we have a matrix, and we can like choose whatever vector I want to multiply.
Yeah.
Like MD kind of thing, right? That's using P. I can choose V any intelligent, like very tricky way.
Yeah.
So does even by like this.
So
arbitrary P does the learn?
So I think basically if the way you are basically the result is that if you are using just this oracle, that random node and transition to a random neighbor. So if you are learning anything about the graph along the way and then updating your queries, this result won't hold. Yeah. Okay.
Random start node was important.
Yeah, that's a very important thing, which I'll tell later. Yeah.
So just to extend this question, do you use vectors EI for your random walk, or do some other vectors?
So basically, yeah, you use I think EI, and then whatever gets multiplied with your matrix, whatever result you get, you will have a bunch of entries. Just subsample one of the entries according to the weights. That's a random walk.
I think here you are assuming that you have an oracle that
Exactly. I mean, I am assuming that, but yeah.
So I think in property testing, it's like a standard assumption. Yeah, you assume you have a random start node, oracle, and a random neighbor oracle. So you are not making any randomness for the start node. That also oracle.
Yeah, that's a random node which oracle gives. Yeah.
So like sparse property testing model, have this access to random neighbor queries. Like you can choose the vertex and get a random neighbor. There are also these queries like DT query, or you can tell like give me like the fifth neighbor. You are not using those queries.
Yeah.
Only random neighbor.
So you can use I think random neighbor query and degree queries. So like for instance, this first result doesn't use the degree queries, but the second result needs the degree queries.
Okay. Yes.
Yeah. So I think I'll show a lower bound against like random neighbor. I think event works for degree because I'll generate a
you can generate simulate like log and type.
Yeah, I mean D-regular graphs. So.
But the applications are you can study this roughly the degree is even if it's not D-regular, but if it's like roughly concentrated around something like as you mentioned social networks are large networks. So yeah, you can bounce. Not exactly, but
Yeah, so I think this kind of models, like very roughly speaking, when to if you want to explore how Facebook networks look, just go to a random person, see their friends, and go on. Yeah. Okay. Okay, so now I want to explain how do they get this result. Yeah.
Sorry, probably basic question. So, if if you go back to where you define the in this, it doesn't matter what the spectral density is. So, irrespective of spectral density,
What?
so if you assume parameterization over the etc., can you do better?
Sure. I mean, if you assume you have some better like. This result for general graphs, but you can impose structure on graphs and then get better results. Yeah. Yeah. I think like for planar graphs you can do something better. Okay. I want to explain how the algorithm works. So now, I want to build up how they came sort of. I don't know if they actually came up with it, but I read it that way. So now your goal is to learn a distribution P. Okay, let's forget about graphs for now. So what do you do when you want to learn a distribution? One of the first things you try is the method of moments. So basically estimate the moments of your distribution. So the jth moment is expected value of x to the j. X comes from P. So then the question is, so my aim is to approximate this distribution P in Wasserstein distance. So the question is, how many moments do I need and to what accuracy? And Kong and Valiant in 2017 showed that if you estimate the first 1 over epsilon moments to exponentially high accuracy, which is additive plus minus 2 to the power minus 1 over epsilon, then you can output a distribution Q such that Wasserstein distance between P and Q is less than equal to epsilon. Okay, so
this is for any distribution?
This is for any distribution. Oh, so this distribution has to be bounded between -1 and 1. Yeah. But yeah, apart from that, doesn't have to come from graphs. Okay, so now we have this result. So okay, by the way, our result shows that this is also tight, and I'll tell what it means later.
N doesn't show.
So there's no notion of n as such when you're talking about distribution P. Yeah, it's like how many moments do you need to estimate? Like if you know that you're coming from Gaussian, then mean and variance are enough. So
it's like a support of it.
Yeah, but this result is general. Yeah, and n is not, and support could be less than n, but yeah.
For intuition, like you said, you have Gaussian, right? You just need 2 moments. Mean and variance, and you get the
Yeah, the support is infinite.
Support doesn't always help for sure.
Okay, so with this result in hand, now our aim is to estimate the first 1 over epsilon moments of P to this exponentially high accuracy. So the question is basically what you're all wondering, hopefully, that how to estimate the moments of graph, like what are your samples here, right? So you're only given random walk access to graph. So for this, basically, there's this amazing relationship between random walks and moments, which Cohen-Steiner et al. Use. So basically, you're given this distribution P, and the jth moment can be written as 1 over n, summation I equals 1 to n, lambda I to the j.
There is no absolute value or anything.
No. Okay. Okay. So this already looks somewhat suspicious, right? Like summation lambda I to the j. You can relate it to trace of a to the j, the sum of eigenvalues of j, and then This trace can be written as basically summation I equals 1 to n ei transpose a to the j ei. Basically, I'm picking the diagonal elements and summing them up. And a to the power j is also related to j length paths, j length walks in the graph. And basically, for a normalized adjacency, you can see that it corresponds to that a to the power j ei transpose a to the power j ei corresponds to probability. The j step random walks starts from I and returns to I in exactly j steps. Yeah.
So, is the algorithm, so the trace connections, are you going to do some H++ type thing to estimate the traces? Because
No.
each moment is the trace.
Yeah.
And you wanted to estimate one
trace
by Bayhound's paper. So is that it?
Yeah, you don't use H++.
Okay.
Use something simpler. Yeah.
I see.
Yeah.
So I think their paper referred to weighted graph. So this will hold.
Yeah.
I understand this will hold for degree, but unweighted.
Yeah, it will hold. Basically, like because there's this notion of probability there. So when you multiply AI times a, the probability gets multiplied. So that's why you get this is the probability that a random walk from I to I.
Where you are taking a step with the probability proportional to V.
Yeah. Okay. So Mj is basically 1 over n summation I equals 1 to n probability that the j step random walk from I returns to I. Okay. Now this I can already read as the expected return probability because there's a 1 over n there. So expected return probability at a length j random walks starting at I and it returns to return probability means it returns to I when I is chosen uniformly at random from 1 to n. Okay, so let's see. So yeah, I'm just going to write this is there. It is the expected probability. So expected Mj is basically expected I. So I is chosen uniformly at random. The probability of the walk of length j ends at I given it starts at I. Okay, so basically what you can do is so repeat some number of times the following process. So choose a random node I, take a walk of length j, and set your random variable xt to be 1 if it returns to I and 0 otherwise. So this xt is a 0, 1 random variable where the probability of 1 is basically a chance that it returns to I after j steps. And basically expected value of xt is the jth moment. And then you can just average all of them and then the jth moment is 1 over t summation t equals sum over t xt. And you can then just apply the Hubding's bond to get that if you choose phi to be greater than 1 over psi square, then you will get your moment estimate to be very close, like within plus minus psi of the actual value. So yeah, this is what they use. They don't use H++. Yeah.
What is that?
It's the faster version of this.
Yeah.
But I'm sure Approach will know.
It's basically like to estimate the trace of a matrix instead of just looking at all the diagonal entries. What you can do is just multiply it with a random Gaussian vector, and that is in expectation equals to trace. So Gi transpose A Gi is G transpose A Gi. Sorry, G transpose A G is in expectation trace of A, and just take that over many samples of G. So this is called Hutchinson's.
It would be like order n time.
No, so you don't basically the complexity you look at is in terms of number of matrix vector multiplications. You don't assume the cost of matrix vector multiplication. Let HUT CH yeah. So And hush, so basically you show that if you want to get epsilon close to the trace, then you need 1 over epsilon square multiplications. And hush plus plus improves that to 1 over epsilon number of matrix vector multiplications. That's it. It's optimal, they show lower bound.
Last year we did.
Yes, so. Okay.
How do you decide capital?
How do you decide what? So you decide what bound you want, right? Like how close you want to get to the moment estimate, and based on that you get the t should be greater than that.
Yes, how accurate
So basically, like here we said that we wanted very high accuracy. So my psi will be 2 to the power minus 1 over epsilon, and then t would be 1 over 2 to the 1 over epsilon. Yeah.
So this analysis will be independent of the W1 distance. Right? The only place where you use it is the Kong Valiant.
Yeah.
So, like, is it known for like similar result as a Kong Valiant is known for other kind of distances?
So our result will show something there. Yeah. And yeah, basically Wasserstein is the right thing to consider. You do not want to consider total variation and KL and stuff. We'll see that later. Okay. So basically, yeah, that's what I said. If you want your error to be 2 to the power minus 1 over epsilon, you get t should be greater than 2 to the power 2 over epsilon. Okay. So yeah, this is their algorithm basically. They wanted to, yeah.
sorry, just understanding this right. So each of the moments you are bounding to 1 over epsilon, and now you want to bound the total earth over distance to also some order 1 over.
So basically, I'm just going to use this result, this gray box. Estimate the moments to additive accuracy 2 to the power minus 1 over epsilon, and then plug in their paper and I'll get a distribution Q. Okay. I'm not going into details of how you do that. Okay. Done this. So yeah, now their moment algorithm is very easy to see. For you wanted to estimate the first 1 over epsilon moment, so take j equals 1 to 1 over epsilon. And for each of them, you take 2 to the power 1 over epsilon number of trials of random walk of length j starting at node I, and output the fraction of random walks will return to the starting random node. So for instance, if you wanted to estimate the third moment, you can start at a random node depicted by red node here and run a random walk of length 3 by these green things. And for instance, you see in trial 2, you return to the random starting node. And in 1 and 3, you don't return. So you repeat these trials 2 to the power 1 over epsilon number of times. And your third moment would be the number of times your random walk returns divided by the number of trials. And previously, as we saw, that you needed exponential number of trials because you wanted exponentially high accuracy. Yeah.
So why can you not run samples which are, let's say, arbitrarily long, some length, and then sample from that power?
Yeah, so you can, but they didn't. I'm just explaining their algorithm. Yeah.
That would potentially get better.
Yeah, so that's what I'm trying to show today, that it's not going to be better.
You take like long path and sample from that.
So, yeah. So is the algorithm clear what they do? Yeah. So now, as some of you are already wondering, what's the scope of improvement here, right? Like they needed first 1 over epsilon moments to this exponentially high accuracy. Maybe you can get away with lower accuracy. Maybe you can estimate higher moments as like something which you were going along in that direction, that maybe you can estimate more than 1 over epsilon moments and each to some lower accuracy, right? Or you can use any other random walk based algorithm. So like they only look at the fraction of random walks which return to the starting node. You lose a lot of information in that, right? Maybe you can use something better. And our result says none of this is true. Like what they do is actually optimal. So this is what I meant. Like our results are tight in their results are tight in this sense. So after this, I'm going to show you how we prove this. So before that, do you have any questions?
Yeah, you think so, right? Will give the
No, actually, like when we started this project, we thought we can get something better. We were thinking maybe you can get 2 to the power minus 1 over square root epsilon or something. Yeah, pretty surprised by it. Yeah. Okay.
And, just to clarify, like the lower bounds that you're going to show hold for this moment estimation based method.
Moment estimation based method, and for the third point, random walk based algorithm. So
for any random,
yeah,
like there is no other way in which I can estimate the distribution such that
I mean, so the thing is like there are two things. So under this model of random node plus random neighbor plus, and also if you want to do better than 2 to the power 1 over epsilon, in that case you can't do anything better. But if you take more than 2 to the power 1 over epsilon, maybe you can do something different, but it won't be better because it's more than 2 to the power 1 over epsilon.
2 to the power 1 over epsilon for each moment.
Okay, so I'm going to show that so initially I said that their algorithm takes 2 to the power 1 over epsilon steps of random walk for each moment. So that is j like 1 over epsilon times 2 to the 1 over epsilon, which is again 2 to the power order 1 over epsilon. So yeah, so this third point will show that there's no algorithm which takes 2 to the power 1 over epsilon steps of random walks any way you want under that Oracle model. It can't do better. Okay. So yeah, and like surprisingly, the construction is very easy. So kind of fun. So formally stating the result that there exists distribution that. So this is a lower bound for learning distribution. Does not have to be graph distribution. So there exists distribution that cannot be approximated to accuracy epsilon in Wasserstein-1 distance, even if you know all of their moments to this exponentially high accuracy, and this multiplicative thing is strictly stronger than additive thing because our distributions are bounded between -1 and 1. And the second thing for learning graph spectrum, basically there exist graphs. You cannot, no algorithm based on 2 to the power 1 over epsilon steps of random walk can approximate the spectrum of G to accuracy less than epsilon. And both results are constructive. Okay. So now I'll show how we construct these distributions. So my aim is to generate two graphs, G1 and G2, that are epsilon far away in Wasserstein distance, and that expected probability of return after J steps is very small, 2 to the power -1 over epsilon. So what this will imply is that the jth moment is within 2 to the power -1 over epsilon from the relationship we previously saw between moments and random walks. With the okay, like basically you return a lot of time. So I'm giving two graphs. You return to the starting node a lot of time, but the difference between these two things should be only 2 to the power -1 over epsilon. So the motivating example for us was basically two disjoint cycles of length L and cycle of length 2L. And so we know the eigenvalues of these cycle graphs exactly. Like, you know, like you can write it also, but I just drew a picture here. And Wasserstein distance between them is 1 over L. L is the length of the cycle. And like a rough way to see is this, that these are sort of they're sort of uniformly spread in between the eigenvalues, they cluster to it. But the eigenvalues of cycle of length 2 will exactly interlaces these eigenvalues. So on average, you have a Wasserstein distance of 1 over L.
sorry, going back, but how does the graph name in the terms of graph translate to?
So basically, it's like the jth moment is probability that a random walk of length j starts and ends at random node I. Okay, and their algorithm needed that you estimate all the moments to exponentially high accuracy. So what I'm going to show is that there are two graphs which are far away in Wasserstein distance, and basically the probability of return. The difference between those things is exponentially low, and that's how you show lower one.
So they were considering only the 1 over epsilon moment, whereas you say for
We show it for all.
Then if you can do this, then automatically.
Yeah. So this
saying is that there are two graphs whose moments are so close. That if there was an algorithm that could have looked at the moments and told you which graph it takes on, that is not possible. So there are two graphs, moments are so close. Therefore, you cannot solve the distinction problems given this.
Yeah, thanks. Okay, so basically, the way to view this Wasserstein distance is that approximately you'll have like the support of this would be around L, and these are sort of like almost uniformly far away, so they're like 1 over L apart, and the eigenvalues of ring of length 2L basically interlaces them. So if you work it out, it comes out to be the Wasserstein distance between them is 1 over L. Okay. And now I'll choose L to be 1 over epsilon, and let's think of it as an odd number. So now my aim is to generate two graphs, just recalling the aim. To generate two graphs that are 1 over L is equal to epsilon far away in Wasserstein distance, and all moments are exponentially close. Okay, so the weight of these purple edges is half. With probability half you can go on the right, probability half you can go on the left. Okay, so now basically what is the return probability? Okay, so there is so return probability of length L minus 1 random walks are the same in both the graphs, because in L minus 1 steps you never loop around in any of the graph. So whatever path you take in first graph you can take in the second graph with the same probability. So this implies that all the first 1 over epsilon minus 1 moments are the same. And now after L steps, so in L steps you can do something unique in this first graph. You can start at, let's say, the first node there, and you can reach back that first node after walking around the cycle in L steps, although with very low probability. But you cannot do that in the ring of length 2L, right? But you have to get really lucky in your random walk that every time you should get like heads L times in a row for you to walk on the ring of length L in clockwise direction or anti-clockwise. But like you can show using standard variance bounds or like mixing time results that L square moments, like the L square length random walk and the L square moments, they are actually very close. So the 1 over epsilon square moment only differs by omega epsilon. So this example doesn't work. So in this example, for instance, I could have looked at 1 over epsilon square moments and maybe have done something better. Looking at first 1 over epsilon moments is like there's something better, more information contained in the higher moment. Is this point clear? So recall that I want this moment difference to be like exponentially small. This is like polynomially small. So now let's think of a hypothetical example. So what's my aim? I don't just want my random walk to revisit the starting node, right? Like I don't want it to loop around, because that was the only case I could. There's something different between these two graphs. Like so for that, what I do is basically at each step with probability half, you get stuck in these white hairs, let's say. Like a random walk doesn't move after that, so it disappears is what I'm calling it here. So with probability half, you can go right or left. With probability half, you just get lost. Okay. So in this case, what happens is that formally it's like each edge has weight 1/4, and yeah, this is not a normalized adjacency matrix. So again, the return probability by the previous argument is the same, that L-1 random walk are the same because you cannot differ between. There's no difference between the two graphs if you take only L-1 steps. And if you take L steps, the return probability is 4 to the power minus L, because the weight of each edge is 1/4, so you have to get really lucky L times in a row for you to loop around. And okay, are people following?
So this disappear meaning what?
Disappear is
Stop the random walk.
yeah. Okay. Stop the random walk. Yeah.
Like a vertex is a very heavy cell. Those are the sheets.
Yeah. Once it's in the self loop, it's not going to come out of that. Yeah.
But all these self loops contribute to the moment then?
Yeah. So I'm just giving this slide for intuition. Okay. So yeah, and also like you can actually see basically now you want to start at a random node and you say let's take a random walk of length L square. Then basically you have to get at no point should you have gotten stuck in these gray nodes, because once you get stuck there, your random walk stops. So and like basically if you do that analysis, and you don't have to do that because there's a simpler way to say it, but in this random walk languages that you can see that all the moments differ only by 2 to the power minus 1 over epsilon. I'll show that later how, but any yeah, like whatever length you want.
Any length over L. Before you said before L-1 they don't.
L-1 they are the same. So this is 0, that's the best. This is something bigger than 0, but still small. What this is what? No, it's not a combination. Like
L-1, this L, and now this one is.
this is like any L square, L cube, whatever.
He asked greater than L. Any does it mean any length greater than L?
Any length greater than L, they differ. Any length less than L, they don't differ.
Okay.
Yeah, I mean.
0 is at most.
Yeah, that is.
So can you tell me how the length connected with movement?
So we had seen this, right? Like, yeah, I mean, just that like. So the J step random walk is equivalent to the L, the length of the random walk I'm talking about there. So if you look at a random walk of length, let's say 1000, and you see if it returns or not, that would correspond to the 1000th moment.
That is for that particular graph construction. It will still work for that very.
For cycles, yeah.
For cycles with the so it will work for this, but it will also work for the.
Will what work like?
That same formula that you had shown earlier.
Hypothetical example.
Yeah.
Will it still work for the hypothetical example in the next slide?
Maybe. Yeah. I think so. Yeah. I'm not sure. Like, I think it will work, but that's not important because it's still like hypothetical. Okay. So now like so this is hypothetical. You guys are not very happy about it. Okay. Let's make this real now. So what I'll do is basically I'll just repeat. So in my first graph, I'll just take 2n copies of length n cycle, and the second graph I'll take n copies of length 2n cycles. Okay, and since these are like disjoint graphs, the Wasserstein distance between them is the same as the Wasserstein distance between cycles of length, 2 cycles of length L and a cycle of length 2L. So, okay. Anyway, so Wasserstein distance between them is big. And now what I'll do is basically to make it disappear, I'm going to add a light weighted complete graph. So it's a complete graph now in G1 and a complete graph in G2, very lightweight. So formally, like so so
node here will connect
everything, including itself. So basically, probability half random walk goes to a vertex of the cycle, and with probability half, it can jump to any random vertex in the graph. Okay, so formally, like the graph G1 can be written as 1/4 of the cycle, and since there are 2 NL nodes, so 1/2 NL of 1/1 transpose. Yeah. Okay, so how does this help? Like, so what happens is, like, think of n as a huge number, right? Now the only way to sort of distinguish these graphs is basically you should not be able to loop around in any one of the cycle, and then you can distinguish the graph. But by adding these hairs or gray edges, what I'm doing is, like, with probability half, you can just jump to any random node and then maybe not loop around there, and then keep jumping around without ever finishing a loop. Okay, so
you still need these pairs.
So this here is basically like showing that's a complete graph. Like, yeah, I broke this graph alone and like, yeah. So don't think of it as here; it's edges of complete graph now. Yeah.
I'm just trying to understand this. So in this case, should there be any distance before L steps of random?
No. This is basically like a cycle. Like L steps is the same.
Yeah, exactly.
Yeah.
And then after L steps?
After L steps, what happens is that, like, in cycle we saw L. If you take L square steps, you can get like the moments are very far away. But here, what happens is that in L square steps, you can never like finish a cycle. Like you can just keep jumping around. So it'll look the same in both the graphs. Like,
yeah, that's what I was.
Yeah, so that's what I'm showing. Like if you do a random walk here, you won't know which graph you are in, and the only way to know is if you loop around one of the cycles. Right. But then the issue is that, like, maybe this brings them far away in Wasserstein distance. So this is the spectral density of the rings without the complete graph, and this is Wasserstein distance is epsilon. So epsilon L is equal to 1/epsilon, and basically when you add this complete graph, everything shrinks between like -half and half, and there's only one eigenvalue at 1. And that's sort of apparent from this formula. Like, since a ring is a d-regular graph, you know that one of its eigenvectors is going to be all ones, and 1/1 transpose is a rank 1 matrix with eigenvector all ones. So one of the eigenvalue changes, but now I have a factor of 1/4 there, so that's why all eigenvalues now just lie between -half and half. And what that does to the Wasserstein distance is just divided by 2, because now everything is between everything gets divided by 2, so Wasserstein distance get divided by 2. So yeah, now I want to show that moments are also like exponentially close. So a very easy way to see is that the difference of the moment is exponentially close. The Wasserstein distance we have already established is big, epsilon/2. And the first 1/epsilon -1 moments are the same, because that's basically following from the ring example we previously had. And now you'll see that all except one eigenvalues lie between -half and half. Right? So, and now we also know this, that the jth moment is 1/n summation lambda I to the j.
Interesting that the Wasserstein distance does not depend on n. You take any number of graphs and still the Wasserstein distance will be the same. Does that play a role in
Yeah, I mean, yeah, you can take graphs of different sizes and Wasserstein distance. You can still calculate. Yeah, that's something nice about this. Okay, so anyway, like we saw here that all the eigenvalues lie between minus half and half, and both of the graph have only one eigenvalue at 1. And the moment is basically 1 over n summation lambda I to the j. So the difference of the moment is basically coming from the mass between minus half and half. And now I know that the first 1 over epsilon minus 1 moments are the same. The difference is 0. And all the other moments are only 2 to the power 1 over epsilon minus 1 over epsilon, because now the mass basically is between minus half and half. So this shows that all the moments are exponentially close. Yep. So that's the lower bound. So this is an additive lower bound example. Yeah.
Does the 1 over 2 come from the fact that 1 is L, 1 is 2L? And extending that question, like if we take L and 3L, L and 4L, would that vary?
1 over 2. Oh, minus half and half. Minus half and half comes from the fact that I'm adding this half of the complete graph plus half of the ring graph. Ring graph basically eigenvalues lie between minus 1 and 1, and now once you divide it by 2, lie between minus half and half. And complete graph only just adds one eigenvalue at 1 and shrinks everything else. Okay, so this was clear. And just to show a multiplicative lower bound, basically the moments we consider are not this centralized moment. We only look at expected value of x to the j. So what you can do is just add some isolated nodes in the end. Right. So these things in the end are not connected to the graph. They are like isolated nodes with self-loop. What you basically get is that you have like 2 NL plus 1 number of disconnected components. So you'll have huge mass at 1. That's going to make all the moments more than half, while the difference of the moments is 2 to the power minus 1 over epsilon. So this shows a multiplicative lower bound. Nothing. It's just nice. And we have the same argument. The eigenvalues lie between minus half and half. Now your Wasserstein distance just shrinks by epsilon over 4, because half of the mass is added there. So you take away half of the mass from the middle part.
Why is it multiplicative?
So basically, like, basically what I'm doing is basically making all the moments bigger than half. So what could have happened was if the moments were 0, let's say, then multiplicatively your bound is very bad. Like it's 0 times what is 2 to the power minus 1 over epsilon. But now you know, just to avoid this 0 thing, you just add extra. There's nothing interesting going on here, but like when you state the result, multiplicative is strictly stronger. So yeah, this is what I have shown now, the lower bound for learning distribution, and you can extend this to total variation distance, scale divergence, and other things which I see in general. Because what you can do is just like make these sort of disjoint support wherever there's the same mass, just remove them, and wherever like you can just make these distributions to have disjoint support without increasing the Wasserstein distance. So total variation you'll get 1, and if it's disjoint support, the KL divergence will be infinity. So this shows it for all. So in that sense, that's what I was saying, that Wasserstein is something, the right thing to consider here. Yeah.
Maybe I missed this. Why do you need n rings and
Basically, the idea was that I wanted to simulate this hypothetical graph. Your probability half, your random walk disappears.
and let's say your n was 1.
No.
Is that just
No. You would need n to be 2 to the power L or something. So basically, the idea was that for the random walk to disappear, I'm just putting it on some other cycle. So just never finishes it. That's all. Okay. And also, the idea for random walk lower bounds is the same, which I've already said, that the only way to distinguish is if you loop around the cycle, and you can show that that's a very low probability event. So any algorithm based on 2 to the power 1 over epsilon steps of random walk cannot approximate the spectrum. Okay. Now the interesting part is adaptive random walks, which is something very open. So now with our results, we've shown that we get tight rates for all random walk based algorithm. And here the starting node was random. But what if you can specify the starting node of your random walk, right? You just say, no, I really like this node, do a random walk from here. And then you're like, no, I don't like the random walk. Basically, I'm calling it adaptive because you can just, your next query can depend on your previous query. So in that case, we prove a lower bound of 1 over epsilon square. Previously, we proved a lower bound of 2 to the power 1 over epsilon. Now we could only prove a lower bound of 1 over epsilon square. And the lower bound.
Model here, you just have start at an arbitrary one.
Yeah, like you can start at a random vertex also, but you can
have the random neighbor.
Yeah, random neighbor. But this is like a sort of abstraction of a very general model, because once, if you don't like a random, you can explore your neighborhood and then choose where you want to go next. Like you can keep repeating the random walk from like query your neighbors, because you can specify the starting node. Based on that, you can guide your random walk.
So what upper bounds node for it?
Yeah, that's the sort of surprising thing that I'll tell that later. But no sublinear time algorithm uses this, where you can specify the starting node. First I'll tell the lower bound. It's very simple. I just think of this as like the graph G1 and G2. So it's like half plus epsilon fraction of 4 cycles, and half. Okay, there should be a minus there. Half minus epsilon fraction of 2 cycles. And in the other graph, it's half minus epsilon fraction of 4 cycles and half plus epsilon fraction of 2 cycles. So now basically both the graphs contain same kind of stuff. The only way to distinguish them is if you figure out this ratio of 4 rings to 2 rings. And that you can basically reduce it to, like, you can say that if you want to figure out a coin of bias half plus epsilon from a coin of bias half, you need 1 over epsilon squared tosses. That's just the lower bound here. Yeah, so this is the question that the best of linear time algorithms only use the non-adaptive random walk queries. These are the 2 algorithms. And yeah, we proved a lower bound in the non-adaptive random walk model, so there's nothing left there to be done. And we proved a lower bound of 1 over epsilon square. It's not known, like, can you do something better? Can you maybe come up with a better algorithm, or maybe prove a stronger lower bound? Yeah, that's it.
So now we'll have some questions. Can you tell very briefly what is the idea of
Braverman basically.
Because it depends upon n, so what is the benefit?
Basically, I think they do something like so. These here we were calculating these moments, right? Like expected value of expected value of x to the power j. Yeah, but what Braverman do is basically they calculate. So instead of x to the power j, you could have put any polynomial in x. So if you put a Chebyshev polynomial, they calculate something called the Chebyshev moments. Yeah, so you don't use this, like, then there's some Chebyshev 3-term recurrence. So you use that and like carefully construct that Chebyshev. Vladimir Braverman, yeah. Not Mark.
Also, like, any kind of lower bounds known for ANOVA epsilon to the power 7?
Yeah, I think we have some preliminary results on proving n over epsilon cube, but Yeah, there's no known lower bound as such. Like, it's difficult to compare this model. Yeah, but yeah, no lower bound. No. I mean, we show lower bound if n is really huge, right? But yeah.
Your graph instructions were pretty cool. You've seen them elsewhere? Or? Yeah, that's the question.
I mean, no.
Very cool.
I mean, no, it's just like, no, I haven't seen it. I just seen cycles before, but yeah. So yeah, I actually saw this tweet on Twitter that there was a cycle on a tree. Yeah, there was a cycle kept on a tree, and then somebody posted a breakthrough result. Tree with a cycle found in IISc. No, just a regular bicycle.
Do we have any more questions? We'll continue this topic. Let's thank the speaker again. And a small token of appreciation from our side.
Here for 2 years and got no.
Yeah. I've been very lucky with t-shirts and stuff. Like, I only have like one NYU t-shirt.